Welcome to the second video lesson on circuit electricity graphs. In this video lesson, I am going to focus on attempting a grade 12 final NSC physics question on circuit electricity graphs that involves EMF and the internal resistance of a battery. So this particular question was taken from the NSC paper, physics paper, November 2014. So if we look at this question, it says that a group of learners conduct an experiment to determine the EMF and internal resistance of a battery. They connect a battery to a rheostat. Now this is critically important because this rheostat is going to enable us to generate the data set. A low resistance ammeter and a high resistance voltmeter as shown in the diagram below. So when we have a setup like this where you have the battery that has an EMF, this one is made up of two cells, and the internal resistance of each of these cells adds up because the cells are in series, then we represent that internal resistance by this little resistor with a small r. This battery is then connected in series with an ammeter, and then there is a single resistor, external resistor in the circuit, as opposed to in the previous video lesson where we had a constant resistor and a variable resistor in series with each other. Now when we have this setup, when we vary the rheostat, you're going to see that the voltmeter and ammeter readings, when they are plotted, are going to produce a graph that is going to look very different to the one that we generated and drew in the previous video lesson. It's not going to look like it is directly an Ohm's law graph, but we'll soon enough see that. So the data obtained from the experiment is displayed in the table below. And something that is important to note here is that as the voltmeter reading increases, the ammeter reading decreases. Now, the way this table has been set up, the left column is invariably the independent variable, and the right column represents the dependent variable. And in this particular case, we can see that the experimenters incremented the voltage reading in a very controlled way by increasing the voltage by 1 volt. Now, that voltage that they were varying is not the EMF of the battery, because the EMF of the battery is constant, certainly over the period of time in which this experiment was done. But when we plot this, we are going to take the voltmeter readings and plot them versus the ammeter readings, as you will soon enough see. So as the voltmeter readings increase, the ammeter readings decrease. Now this immediately shows us that this cannot be direct proportionality, and so cannot explicitly be following Ohm's law. Yet Ohm's law is embedded in the theory of EMF and internal resistance. So now it asks us here, state one factor which must be kept constant during the experiment. Now, when you do this experiment, and a lot of schools do this experiment as one of the NSC matric portfolio practical investigations, when you do this, one of the things you should be very careful not to do is to allow the current to run for too long, because it heats up the resistor. So one of the factors which must be kept constant during the experiment would be the temperature, ideally the temperature. So by keeping the temperature constant as best as you can, you are working within the realms and limits of Ohm's law. Another factor which should be kept constant is the battery. You shouldn't change batteries, because by changing batteries, you're probably going to change the internal resistance of the batteries, because even though they're the same make and they were made to have the same EMF, let's say each of the cells was 1.5 volts, and you put them together, your EMF would be 3 volts. They may be of different ages, and eventually, if you've used a battery for long enough, the EMF is going to drop as it converges on getting more flat. But also, the internal resistances can be different. So by fixing the battery that you use, you ensure that you don't bring in other variables. Now it asks us, says, using the information in the table above, plot the points and draw the line of best fit on the attached graph paper. Now, they have not been explicit here on what you should plot. So this can be problematic because looking at the table, the ammeter reading looks like the dependent variable and the voltmeter reading looks like the independent variable. And we normally plot dependent versus independent. So it's really very important that you plot the voltmeter reading versus the ammeter reading in this question. And this should have been more explicit, but in prepping and preparing for your matric exams, know this, that when you're working with EMF and internal resistance of a battery, and you're being asked, as you are asked in the third part of this question, use the graph drawn to determine the following: the EMF of the battery and the internal resistance of the battery. You need to plot voltage versus current. So let's start off now with the laying out the graph, with looking at the title of the graph as well as the labels of the axes and the scales. So first things first, we're going to give this graph a heading. We're going to say it's the graph of the voltage versus the current. So here we are explicitly showing that we are working with the voltage as the dependent variable and the current as the independent variable. So now we go to the axes. So I'm going to start with the x-axis or the current axis. So I'm going to draw a line there, and we are going to label that. It's going to be the current. So that's going to be the current, and that is going to be in amperes or amps. Okay, and then we are going to look at the scale. So if we look at the data, we can see that the data runs from 0.58 to 0.14. This is now, we're going to put the ammeter readings on the horizontal axis. So the maximum value in our data set is about 0.6. Now, we are going to need to extrapolate this data so that the line of best fit extends to the x and the y axes. So we're going to need to go bigger than 0.6. So if we look on the horizontal axis, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 of these big blocks. So we've got more than enough space to include 0.6. Now, the idea when drawing a graph is to draw it as accurately as possible. And it's way more easier to draw a big graph accurately than a small graph. Because you're not going to plot the data 100% accurately. But if you do it on a small graph, then whatever error you make is going to have a bigger impact. It's going to be a bigger error because you're multiplying by more. Your scaling factor is more. So if we look here, if I go 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, that would work nicely. So that's what we're going to do. So we're going to have 0 here, this is going to be 0.1, this is going to be 0.2, this is going to be 0.3, this is 0.4, this is 0.5, this is 0.6, this is 0.7, and this is 0.8. It's always very important that there's consistency of scale. So each of these double blocks is going to, on the x-axis, is going to represent 0.1. Hence, each of the blocks will then represent 0.05. So just explicitly, I'm going to put that's 0.05. That's going to be 0.15. This is going to be 0.25, 0.35, 0.45, 0.55, 0.65, and 0.75. And it's critically important that you get your scaling right on your axes and that you label them correctly with the units. Now we go to the voltmeter readings. If we look at our data, we'll see that our voltmeter readings go from 2 to 6. So we're going to need to incorporate bigger values than 6 because we're going to need to extrapolate this graph to the y-axis. So if I look on the y-axis, on the vertical axis, I'm going to firstly draw a line to represent it. So the line's going to be there. Right, and this is going to be, we're going to label this axis, this is the voltage. So this is going to be the voltage in volts. And so we look at this now and we say, okay, we need to fit 6 in. Now if you look, you can see we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we can't quite work with fitting in working with 2 blocks per 1 volt because we would need 12 blocks. So we're going to then, I'm going to work with just each of these big blocks representing 1 volt. So that's 1.0, 2.0, 3.0, 4.0, 5.0, 6.0, 7.0, 8.0, 9.0, 10.0, and 11.0. Right, and that's going to be 0 there. So now we have our axes labeled and scaled, and we have the heading. So now we can plot the data. So the first point we're going to plot is 0.58 and 2. Right, so if we look at 0.58, 0.58 is somewhere here. So looking here, this is 0.5, this is 0.5, this is 0.55, so this is 0.56, 0.57, 0.58. So we are going to extend a dotted line upwards in that way. And the voltage is going to be 2. We can see we're plotting this point here, 0.58 and 2. So now we go to the voltage axis and we are going to extend a horizontal line to the right until it meets with the vertical line, and there is our intersection point. As discussed in the previous video lesson, we are going to put a circular region of uncertainty around that data point. So we qualitatively acknowledging that there's an uncertainty in the independent and dependent variable. By qualitatively, I mean that we're not going to physically work out what the uncertainties are in the horizontal uncertainty and the vertical uncertainty in our data point, which one would do, for instance, in a further studies in physics course. Now, let's take a look at the next one. The next point is going to be 0.46 and 3. 0.46 and 3, so we go to the x-axis, the current axis, 0.46 will be there. Right, you can see this is 0.45, that's 0.46, 0.47, 0.48, 0.49, 0.5. And then we go to the voltage axis and we extend there. We're going to extend there 3, and where they intersect, that is going to be where the data point is with the region of uncertainty around it. So we've done that one. Then we're going to go to 0.36 and 4, 0.36 and 4. So we go 0.36 is there. So we go up 0.36 and 4. We're going to extend the horizontal line to the right. And so our data point is going to be there with the region of uncertainty around it. Then we're going to look at 0.24 and 5. 0.24 and 5. So the scale is working really nicely. It's making it quite easy for us to find the points, the values for our x and y points, for our current and voltage points. So this is 0.24. We extend up, and we are going to extend up to there. 5, we now go to 5, which is there, and we extend to the right, and there's going to be our data point with the region of uncertainty. So we've done that point, and then last but not least, 0.14 and 6. So we go to 0.14. So this is 0.11, 12, 13, 14, 0.14. So we're going to extend up there. We're going to have to go quite high, so I'm going to zoom out a bit. We're going to go there, along that line, until we get to 6. Right, and yeah, it is 6. So there's our point, and we now plot that, and we can see that the tendency is that as the current values increase, the voltage values decrease, and it does look like there's a linear pattern to this data. So now I'm going to draw a line of best fit, and I'm going to draw a line that goes through there. I'm going to try to make sure that that line is a good representation of the average of the data. Now, the line of best fit need not go through any single one data point. As a rule of thumb, you want to have as many points above the line of best fit as below it. But that's a qualitative way of doing it. A more quantitative way and a better way of doing it would be to use linear regression, which is outside of the scope of the syllabus, where you would plug the x and y values of the data points into this formula, and it would then give you the gradient and the y-intercept of this linear fit, hence the equation. So let's just see, I've rubbed out that there, so I'm going to add that. So now we look at this, and this is the data set is this set of points. Now, what we want to do is we want to use the pattern that we have now identified in order to extend the lines to, in particular, to the y-axis. You'll see why just now, and generally to the current axis as well. So when you extrapolate, it's good to take it to the axes. So now let's do that. So I'm going to go now, and I'm going to extend this line. Right, that's not a very good attempt. So I'm using a drawing tool on my iPad. So I now try again. So I'm going to put it there, and I extend there. And so you can see now that our y-intercept is going to be there. So we're extrapolating the data. Then I'm going to do the same at the bottom here. And I'm going to extend the line there. And so this would be now our x-intercept. Right, so now this particular problem was a 7-mark problem, and in this particular exam, so it came from a matric exam, so the mark allocation would be less than, say, for instance, if you were doing this in grade 10, where we would assign more marks. But this, in a grade 12 exam, 7 marks, so I would surmise that there would be a mark for each of the axes. That would be the scales and the labeling. Then for the data, 3 marks for the data points, and 2 marks for the line of best fit. So that would give us 1, 2, 3, 4, 5, 6, 7. However, it could be that and I haven't looked at the memo, it could be that only 1 mark for the line of best fit, and then there would be a mark for each of the labels and maybe a mark for the scales on both. It could be that there's a mark for that one of these marks is there. So it doesn't really matter. The important thing is, good practice is to always put in a title for your graph, a graph of dependent variable versus independent variable. You're not necessarily aware of exactly what the mark allocation is. It varies. And then each of the axes, you have a label with the particular unit that the data has been collected in and that you're plotting. You have constant scale, consistent scale, constant scale on each of the axes. The scales don't need to be the same for the x and the y axis, but they do need to be consistent throughout each of the axes. So now that we've got that, now we can go and we can answer the questions that follow. So we now are asked to use the graph that's been drawn to determine the EMF of the battery as well as the internal resistance of the battery without using any form of the equation EMF equals IR plus little r. Now, what they mean by that is they do not want us to take points and substitute it in here and set up simultaneous equations in order to get little r and the EMF. They want us to use the properties of the graph. Now, the graph is a straight line, and we have V plotted versus I, but it also is a graph, a line with a negative gradient. So this particular graph is not a simple straight line which has a 0 y-intercept of the form y equals mx, because the y-intercept is 0, but rather this graph is going to be of the form y equals mx plus c, where c will be on the voltage axis. So what we need to do here is we need to take this formula that you find on the formula sheet, and we need to convert it, transform it into y equals mx plus c. And that's what I'm going to do. So say, right, so the EMF is I total times R plus the internal resistance. I'm going to multiply the I through, I'm going to distribute it through the bracket, or into the bracket, so we're going to get that the EMF is IR plus I times little r. This is the external voltage, or the operational voltage, which is in actual fact the voltmeter reading in our circuit. This is the total current, and that's the ammeter reading. So what we're going to do is we're now going to make V the subject of this equation. So I'm going to do it by taking this across to the other side. So we're going to make that minus IR, little r, plus the EMF is going to equal V, external V operation, I'm just going to call it V, because our dependent variable is V. That's the V axis, the dependent variable axis. So this is going to be like Y. Right, so we're going to write it as V, and I'm going to use color. V equals minus R, and there's a reason why I'm switching these two around, minus R times I. We should know that I times R and R times I is the same thing. And then we're going to have plus the EMF. Now, if I write it in this form, Y equals mx plus c, then from this we should be able to see that the negative of the internal resistance equals the gradient of the line, which would be y2 minus y1 over x2 minus x1, and that the y-intercept will be the EMF, which should make sense because the y-intercept is sitting on the voltage axis and the EMF is a voltage. It's the theoretical voltage of the battery. So with this now, we can now move back to our graph, and using the gradient and the y-intercept, identifying the gradient and the y-intercept, we can now work out what they are from the graph. So now what we're going to do is we're going to choose 2 points that are convenient to read off this particular line of best fit, and it really is up to you which points you choose. I'm going to choose this point here. I'm going to choose this point, this one here. I'm going to open it up like that. I'm going to use a square around it just to identify that that was not an original data point, and it's a point on the line of best fit. And if we look here, if I drop a perpendicular to the x-axis, I see that this is 0.1. Remember, it's 0.1 ampere. And if I drop a perpendicular to the y-axis or the voltage axis, then I see that that is going to be 6.2, 6.4, 6.6, 6.8, 7. So that's going to be 6.4. And remember that that is a voltage. Then I choose another point that I'm going to find convenient, and I'm going to choose this point here, which is very, very close to one of my data points. Right, I'm going to go down. I'm going to call that B. We're going to call that B, and B is going to be, if we drop a perpendicular down, we're going to see that this is 0.35 amperes, and the dropping a perpendicular to the y-axis, that's going to be 4. So that is going to be 4. Right, so we've identified 2 points on the line of best fit. I'm going to call this point x1, y1, and this point x2, y2. And now using those 2 points, I'm going to work out the gradient. Now, remember we said that the gradient m is equal to the negative value of the internal resistance. So this can equal m, which is going to be the change in y, y2 minus y1, over x2 minus x1. So y2 is 4 minus y1. y1 is 6.4. We can pick it up there. So that's going to be 6.4. All right. And then divided by x2. x2 is going to be 0.35. 0.35 minus x1, which was 0.1. 0.1, we can show it there. So x1 is 0.1. So there we go. And so now keep in mind that this is a voltage. and this is a current. And so now we are going to work this out using our calculator. So 4 minus 6.4 gives us negative, this gives us negative 2.4 volts. And 0.35 minus 0.1 is 0.25 amperes. So negative 2.4 divided by 0.25. And that's going to give us that the negative internal resistance is going to be equal to negative 9.6 ohms. And so R, we remove the negative by timesing by negative on both sides, or dividing by negative 1 on both sides. We're going to get little r is 9.6 ohms. So that is the internal resistance of this battery. When it comes to the EMF, all we need to do is we need to go to the y-intercept. And so going to the y-intercept there, we can read off this is 7.2, 7.4, 7.6, 7.8. So this is going to be 7.4. And so our EMF, but it's important that you explicitly show how you're getting the EMF, that the EMF is equal to the C, which is the y-intercept, which is 7.4 volts. Now the mark allocation was for the EMF was 2 marks, and for the internal resistance was 3 marks. So this would be 1 mark, and it's important not to leave out the negative. I found over the years that learners leave out the negative. They get this right, but they get this wrong. So make sure it's the negative of the internal resistance, because the internal resistance is positive, but your gradient is negative. So therefore, your negative gradient must equal the negative of the internal resistance. There will be a mark for the substitution and a mark for the final answer, where R is equal to 9.6 ohms, and 2 marks for the EMF equaling 7.4 volts. And so I hope that this video lesson will give you more confidence when you encounter these graph problems in your examinations and in your tests, and that it has pulled together your knowledge of how you work with straight lines, y equals mx plus c, the gradient intercept form that you learned in mathematics from grade 9, and how we use a linear fit in order to model the relationship between the voltage and the current in the circuit that was presented to you in the question. Now, something I would like to just mention to you before we end off is that just to try and explain why this graph doesn't look like an Ohm's law graph. And the reason is that if you look at the EMF, if I were to draw the EMF, if there was not an internal resistance, then the voltage that would be measured across the battery and across the external circuit would be 7.4 volts, which is the EMF. But because of the internal resistance, whenever current flows, there is a certain amount of voltage lost internally in the battery. And that lost volts is the difference between, this lost volts is the difference between the EMF and the actual voltage reading at that point, which is V external, V operational. So Ohm's law is actually to be found in here because the V last can be explained or described in terms of Ohm's law. V last is I total times the internal resistance. And what we can see here is that as we move along here, as the current gets bigger, the V last gets bigger, because V last is I total times the internal resistance. Now, if the internal resistance is constant because you're not changing the battery, obviously we're assuming you don't overheat the battery so that the resistance increases, then if the current is increasing, the lost volts increases, which means that your operational voltage, which is what your voltmeter across the battery and the external circuit is measuring, is going to decrease. So even though on the surface this graph doesn't look like it includes Ohm's law, embedded in it, behind what you're seeing, is in actual fact Ohm's law. And that's Ohm's law being applied with inside, internally in the battery. And so some teachers actually label this as V internal, which means the voltage loss inside the battery. So I hope that this video lesson has given you the confidence and also the insight into these types of graphs. But practice makes perfect, and so my advice to you would be now to go to the NSC website and to go and find these problems, these types of problems in past exam papers. Thank you very much for viewing this video lesson. I hope you enjoyed it. Bye-bye.